So today I will try to talk about Wilson loop. I still have a few things to say regarding last lecture, which I didn't finish on time, unfortunately. So here is a brief recap, summary of roughly what we covered last time, introduction to the subject. We started with our amplitude, decompose them over a particular basis, a color basis, which is provided by this single trace over there. And neglected everything else, double trace and so on, the non-planar correction, because they are currently out of reach. Then to simplify further, what is called color order amplitude here, we introduce these spinor helicity formalisms, where we recast our momenta and our polarization vector in terms of two-dimensional spinors, this angle and square bracket here. And we try to do something with these formalisms at tree level, examining the simplest possible amplitude and trying to convince ourselves that some of them ought to be zero. If we are smart enough to choose carefully this residual gauge, there is a freedom Q here. We convince ourselves that we could put all this amplitude with one carrying all the same helicities, or all of them except one carrying the same helicities to be zero. And we cannot get farther than that, but one goal was to actually compute explicitly one amplitude for n equal 4 here, so for 4 gluons, which deviates from this series of zeros, so the case of so-called maximal helicity violating amplitude, where we switch one more gluons. This time it is no longer zero, it is not possible to play with the reference spinor to cancel all Feynman diagrams, but we can still cancel a few of them. And in the case of 4 gluon, we will be left with a single diagram. So you can find this down in the paper by Lorentz, which I've mentioned yesterday. And then you can, so it's a good exercise for you if you want to practice a bit with these formalisms. You can take these diagrams, which for 4 is just a diagram like this. Okay, perform the contraction, see that it is proportional to contraction of some epsilon and some epsilon with the momenta. Use these formalisms to perform all the contraction, and using also conservation of total energy and total momentum, bring it to this form, which was first conjectured by Park and Taylor. So there is a generalization from n equal to 4 to any n in this particular class of amplitude, this class of MHV amplitude, and the result takes this very elegant and compact expression. Okay? And there is a lot to say about this expression, about its physical content and so on, but it's not really the purpose of this lecture to scrutinize it. But if you are interested in learning something about it, I refer you to this review by Helwang and Wang, where they will give you an inductive proof and also an introduction to the so-called BCF-W recursion relation, which is to date one of the most efficient way of computing amplitude at tree level. The main idea being to try to use the most elementary possible amplitude, meaning the smallest non-vanishing amplitude, combine them together in a smart way to build up bigger amplitude. So this idea of starting from something which is small and well understood and go to something which is bigger and at first sight not completely understood will also come back later on, but in a different form at group level. Okay? So I recommend this to you if you want to learn more about it. The last thing that I wanted to say regarding this tree-level analysis is mention supersymmetry. So we convinced at tree level we could establish this identity, but it is not clear whether this identity will hold true at loop level, for instance. And this turns out to be the case, meaning that the first interesting amplitude for us will be this class of MHV amplitude. Also at loop level, we will never have to consider this amplitude. And this has to do with supersymmetry. So in n equal to 4, we have a lot of supersymmetry, and all the states in the theory fit in a single CPT conjugate multiplet. Or super multiplet. So this is clear if we use some sort of on-shell superfield. This is just a convenient way of packaging together all the degrees of freedom of this theory, which all belongs to the same representation, the adjoint representation of the gauge group. So what people usually write down for this on-shell supermultiplet, which only collect on-shell states. Okay, so this is not an off-shell n equal to 4 superfield, and I will not know how to make sense of such a formalism. As far as I understand, it's something complicated. But on-shell, at least, it's pretty clear what we should do. If we start, for instance, with this gluon plus, which is roughly, you see, our background we start with all the time. We could also, of course, start with minus. It's related by parity. It's a choice that we're making. Then we can use some supercharge to lower the helicity and get some gauge, which have helicity 1/2. Okay, and if we keep going like this, we will then obtain some scalars, which I denote by Z. Okay, so this A here, sorry, I should have told you, run from 1 to 4. Okay, this is so because we have 4 supercharges, so I can choose 4 different ways of lowering the helicity, which means that this object belongs to a particular representation of SU4 also, which is the R symmetric group associated with this n equal to 4 algebra. Okay? So if I do it twice with this Grassmann parameter, here I get something which is antisymmetric, so this object should be antisymmetric, it should have 0 helicity, and it should be a scalar, okay, from the statistic point of view, a boson. So these are just a parametrization of the 6 scalar field. 6 scalar field of n equal to 4. And then we can keep going like this, because we haven't yet reached the point where we are completely annihilating the state. So we can now put one more eta and derive the conjugate field to this gauge, which is in the conjugate representation of the R symmetry group, and which has helicity -1/2 in my notation. And finally, the best I can do is to put 4 etas together. This gives me a singlet with respect to the R symmetry group. This should have helicity -1, and this is nothing else than my gluon with helicity -1. So there is only one component, as you can convince yourself, with A, B, C, D running from 1 to 4. I can only form one combination here, and this combination, if you want, I could rewrite like this. 1, 2, 3, 4, this is the only object, like G minus. Okay? So I can act with this field with some supercharge. If you want to see the realization of the supersymmetry explicitly, you will define some supercharge. So let me define them like this. So that would be, if I have many of the superfields together, that would be a sum over individual supercharge, say. Let's imagine we have n gluons in our state. N super gluon. Okay? Then I will define the charge like this, with the elementary charge being given by I times derivative with respect to eta. I have also the conjugate charge, which has the same expansion. But this guy now is multiplication by eta. Okay, and you can check at this level that indeed the anticommutator of, I want it like this, will be given up to delta function to to this guy, which one I need to reverse, which is just the momentum I in this spinor notation. Okay? So this is nothing else than writing down on a single line in a single object some things that we know from the very beginning. Okay? So what is nice about it is that we can immediately see, for instance, that the all plus amplitude should vanish. So what we do is that we use the fact that the amplitude should be annihilated by our supercharge. So if I use, for instance, the supercharge Q tilde, which I act on an amplitude, so let me choose the first one. So I have 4 of them. Okay. So if I choose the first one and I put a gaugino here, with the rest being a bunch of G plus, then this should be 0. Acting on this guy, I'm just bringing this guy up. Starting from here, I go to this guy here, which means that this is nothing else than my all plus amplitude up to a factor which I forgot here, which I will put here, which is 1. Okay, I act with this guy here on the first guy, so I pick up some helicity because this guy has helicity. Okay? So except in the exceptional situation where this will be 0, you conclude that this amplitude should vanish. Okay? It is no more difficult to consider the case where we have all but 1 plus. What we will do is that we will proceed similarly, but we will put a G minus at the beginning. Okay? And then we will put our psi minus, our psi 1, sorry, some G plus, some G plus. Now we need to act, sorry, I didn't tell you, maybe I should. So this guy acts on this one, but of course there is a string of action. I should act on all the state one after the other. This is a sum of individual action. But this G plus is the top component. I cannot go further. I cannot increase the helicity further. Okay, so this guy, this just go through and I just act on this guy.
It looks like Q ways the tilde multiplied by 8.
So if I act with Q on this guy, I am taking derivative. Which means that Q, then I differentiate everything. This guy disappears. This guy becomes the bottom or the top component because I differentiate it. So in terms of field, it means that acting with Q on G plus gives me a psi. Okay, so why the other way around for Qt? Yeah, it's a question of okay, this dual action, whatever. So what do we get in this case? Now we have to act on this one and on that one. So we act on the first guy, we get again this one. Okay, then we have an amplitude A, psi 2, 3, 4. So I remove this, I remove one index here, I go to this guy which has three indices. Then I have psi 1, a string of G plus. And then I need to act on the second. So I have a 2. And I have G minus. On the second I know already what is the same as here. It gives me another G minus, G plus, G plus. Okay, and this should be 0. So that gives me, before I had only one term, so it was obviously vanishing. Now I get 2 terms. So what I can do is, for instance, I can project on the left with 1. So we can multiply everything by 1. Okay. 1, 1 is 0 because my excitation is on shell. Okay, so this, you remember this bracket ij is minus gi. So So that should vanish. That kills this component. Then here I get 1, 2 times this. So except if 1, 2 again exceptionally vanishes, the amplitude should vanish. Okay? Is it clear? It's very simple. I'm not sure I'm saying it in simple terms, but it's very simple. So I project, I kill this term, I pick this one, this is equal to 0. Ah, sorry, press. Q. Q tilde on psi 1 is the same action as here. Give me plus. So 1 minus and all plus is 0. So it starts to be more interesting, as you might understand when you consider MHV. Because when we consider MHV, now we will start with 0 is equal to Q tilde 1 acting on A. I will put 2 minus at the beginning. Then I will put my spinner again and a bunch of pluses like this. And I will go through. And I will find 1, A. So there are 3 terms. Do we have all of them? So this is the same as before. And that is 2. This is G minus, psi 2, 3, 4. Minus, G plus. Then there is 3. G minus, G plus, G plus. Okay? So I got the amplitude I was interested in. The amplitude with 2 minus gluons and a string of pluses. But now I see that I have 3 terms. So in particular, I could kill this amplitude if I want by projecting against 1. But this is not going to cancel everything. Okay, so I will now be left with a relation between this amplitude and that one. Okay, so this relation reads A G minus 3, 2, 3, 4 psi 1 G plus is equal to minus 1, 3, 1, 2 A G minus, and G plus. So this is what I got. So for MHV, supersymmetry cannot be used to involve some cancellation. So here I should have stressed that I was using only one charge, one type. Here I was using only one possible value for the index, which means that this condition, that the amplitude, this amplitude, and that one vanish, is true in any theory which has n equal 1 supersymmetry. N equal 4 here was not needed to establish this cancellation. So you see that if you plug Park-Taylor here, what this is doing is that it is removing one factor 1, 2. So we will be left with 1, 2 to the 3. And we replace this factor 1, 2 by factor 1, 3. So this is how you can write down this amplitude which involves some gauging. Okay. So this is still an MHV amplitude. You see essentially what we are doing is that we take a pair G minus G plus, okay, and we just reshuffle the helicity. Okay, so we bring a bit of the helicity from one to the other. So this guy in particular will have the same helicity as this pair. This is minus 1/2, 1/2, and this is 1 minus 1. So I'm just, essentially what I'm doing is what you would probably have expected from the very beginning, is that supersymmetry allow me to change the flavor of the state. Okay? But it preserves the total helicity of the object. Okay. So now what happens is that when we have more supercharge, we can keep playing this game. So now what I could do is that I could use Q2, start from a properly chosen amplitude, and derive a new relationship. So now what I could do is to, what can I write down? Maybe this I can erase. Now what I can do is that I can, with more supercharge, I can go from gaugino to scalar, roughly. And because I have a relation between my gaugino pair and my gluonic pair, I will end up with a relation between the scalar pair and the gluon. Okay, I just write down the final expression. You can play this game or open a review and see how they do it. It's very not difficult. Or you can reverse engineer if you want. What I'm writing. So now I have a pair of scalar field, and this pair is 1, 3, 1, 2, now square. Okay. So you see, it's a fun game. You are just changing a bit this. The numerator is always the same. You can keep it like it is, and we are just changing a bit the denominator, sorry, it's always the same. We are just changing the numerator a little bit, depending on what kind of flavor we are scattering. So now you understand that with n equal 4, supersymmetry, I can relate, I can go all the way from plus to minus, and so I can derive that g plus g minus, if I apply this trick again 2 times, I can now have something in which I have flipped the g minus and the g plus. So this is telling you that the position of the minuses in the background of pluses is not so much important. It boils down to replacing the numerator, which was 1, 2 in this case, because we have 1 and 2 being minuses, now which become 1, 3 to the power 4, because 1 and 3 are the carrier of the minus helicities. In other words, if you keep playing like this, you get a more general formula. This is EF position. You get that this is ij to the 4 divided by 1, 2 to the 4 times an g minus, and g plus. Okay? So supersymmetry is telling us that there is a lot of redundancy in the amplitude, and it does not really matter where you put your minuses, at the end it's the same object. And again, these relations are exact. It's not something which apply at 3 level. You could check it at 3 level, of course, but it's not, it does not rely on perturbation theory. It is a consequence of supersymmetry, so it is a consequence of the fact that you have this n equal to 4 supersymmetry, and the fact that the vacuum is also supersymmetric. Okay, I use it implicitly for the condition that my amplitude should be annihilated, which is the same as saying that you represent the amplitude by a string of operators that act on a vacuum. You sandwich with the vacuum on the other side, and then you put some charge in it, and you know that the charge should annihilate the vacuum, so it should be 0. Okay, so what we get is a sort of super Park-Taylor formula which we can write like this. So now it's a super MHV amplitude. I don't know where to put the S, but you understand. The argument are this super field instead of, you don't have to pick a particular. I'm also putting back the conservation of total momentum. There is a Park-Taylor prefactor, which you remember is the same for everyone. And then there is the numerator, which we can write as a delta 8 of q tilde, which is conservation, if you wish, of it is a supersymmetric version of the conservation of the momentum, times some Wn. I will comment a bit on it. So this is just conservation of momentum. This delta 8, well, you know that delta function for Grassmann variable is just product with the Grassmann parameter. So this is in fact nothing else than a product from all the possible supercharge. How do I write it like this? A dot. So I need to contract over the spinor index. And this you can also write, if you prefer, like product again of some ij times eta ia, eta ja. Okay? It's just a big object which will start like this: 1, 2 to the 4 times eta 1 to the 4, eta 2 to the 4, plus etc. So it's an object which has which is of degree 8 in the etas, which is what we need. For this MHV amplitude. Okay, this is each time I have 4 etas here, we are changing a G plus into a G minus. So for MHV, I need 2 times 4 etas. Okay, and that's it. And then what we expect, what we want for the MHV amplitude, is that the full object here are actually only 8 etas, which means that this Wn over there is just a bosonic quantity which does not know about the flavor of the excitation that you are scattering, meaning that you can choose the one you want from the very beginning and compute this W. Okay, it will be it will then be it could then be applied to any scattering process just by dressing it by this delta 8. So this delta 8 takes into account the difference of flavor for MHV. Okay, this is nothing else than saying that this delta 8 is such that it is annihilated by the q tilde. Okay, because I'm already saturated in terms of q tilde. So if I act with q tilde on this delta 8, I get 0, and if I act with q on this delta 8, I also get 0 because of conservation of momentum. So, in other words, the condition that Q annihilate A is a condition that this equals 0 is a condition that Q annihilate Wn. And again, in the case of MHV, the solution is trivial. It's just to say that Wn is a constant with respect to the etas. Okay? Because I have already the right amount of etas. So for nk MHV, which will correspond to flipping more gluons. For instance, if I want now to consider a scattering amplitude where this G plus is becoming a G minus, I will need more etas. Okay? I will need, for instance, eta 1, eta 2, and I need an extra factor that give me, for instance, eta 3 to the 4. Because eta 3 to the 4 will precisely mean change G plus into G minus. Which means that when you consider AK, where K is for next to the power k MHV, which means turn more and more G plus into G minus, if you prefer, then this will again be written like that. But then this W will no longer be a bosonic factor. It will be a polynomial of degree 4k. Okay? So NMHV, which is the next case to consider, will involve a polynomial of degree 4 in the etas. Okay? And in general, you can there can be many solutions you write the most general polynomials, and then you impose a condition that it is annihilated by Q, and you look at how many solutions you have. So MHV is exceptional in the sense that it's a polynomial of degree 0 in the etas, so there is only one solution if you prefer, but for higher value of k, you can in principle find more structure. which is why, from our point of view, it's a more complicated object. We could try to address it, we could address it actually, but it's obviously not the simplest thing to consider. Okay? So is all of this clear? Because this is roughly the conclusion of the first lecture, which is, so I remind you that the first lecture was what is the simplest scattering amplitude in this n equal to 4 superior mills, and the answer is essentially this MH. So this is the simplest non-trivial quantity to consider, and now the goal is pretty simple. The goal is to compute this WN. So what we know from Park and Taylor is that W1 is equal to 1. This is tree level. But then it will receive correction. It will receive correction loop by loop, where lambda is the Taft coupling. Okay? So this is our goal now, to compute this WN. So we got rid of almost all the complications, the colors, the helicity, and so on. And now we can focus on a purely scalar quantity. But it's still a relatively complicated object because it's by Lorentz invariance. It can depend on all the possible Mandelstam invariant for my process, and you know that there are many of them. When the number of particles you are scattering is large, there are many Mandelstam invariants you can form, independent Mandelstam invariant. So it is in general a complicated function of the Lorentz invariant kinematical quantity and the coupling. So it's not obvious how to proceed with this problem of computing it. Of course, you could draw some Feynman diagrams and eventually compute loop by loop, but as you might guess, it is relatively hard to do it. And the goal of this lecture is to learn how to do this kind of analysis without using Feynman diagrams. It's in the spirit of integrability not to use Feynman diagrams, but find the proper integrable description of our object and just use integrability as a guide for solving. Okay? But actually what I should say is that 10 years ago, some people, Baird, Dixon, and Smirnov, wrote a no-loop formula for this WN. It looks like the problem is already solved. This is called the BDS ansatz. And essentially, what this ansatz is saying is that let's take the case of 4 gluons, the first case to consider, in principle the simplest in this series of objects. Okay? So their claim was that take the log of this WN. This is something that starts at one loop. Their claim is that it's no more than the one loop result, which is given by this so-called box diagram. So here the rules of the game are the same as for scalar theory. Okay, there is these vertices which are just weight 1, and then you just put all the propagator, and you compute the integral. It's an integral over 4. There is form 1 over q squared in the game, and then there is this st, which makes the object properly normalized in terms of dimension, which this should have dimension 0, okay, which is the case with this st in front. St are just the Mandelstam invariant. So S, let's say that S is this, and T is that. Okay? And then there is a coefficient in front. At one loop, this coefficient is directly related by lambda. Okay, and it could be in some world that actually this one loop result after exponentiation, because this is what this implies, will be the complete result. But it's not quite true, as we will understand. But the recipe was roughly speaking, that you should replace this coupling lambda by something which is a cusp anomalous dimension, okay, which is a quantity that that already appeared yesterday. If you remember, Collier mentioned the fact that Wilson loop with cusp might have divergences, and these divergences are controlled by some anomalous dimension, which is the so-called cusp anomalous dimension. So this is a bit sketchy, but this is roughly what they claim. And there is something that you could immediately complain about if you are a bit familiar with Feynman diagrams, is the fact that this diagram here is not finite. So this diagram has infrared divergences. Okay? So these infrared divergences looks like a problem because so there is. Okay, I write the divergences. Because we have divergences, we need to introduce some regulators. This is a mu. Just playing this wrong. And then behind these divergences, if you dig out, sorry, it's log square. Plus some dots. There will be a finite piece. I'm actually thinking that I forgot to put a divergence here. So this, wow. Let me write it like this. Let's say I put a hard cutoff. Okay, so I have a log square of lambda. Lambda is my hard cutoff.
Can I ask a question?
Yes.
This diagram is for scattering of gluons.
Yeah, this describes the scattering of gluons, but this diagram you can forget about your gluon to compute it. It's literally just what it means in terms of scalar in the scalar theory. Okay, so you have a vertex which just give you 1, like a phi to the cube, and then you have propagator which are 1 divided by p square minus 0, in this case, p square plus I epsilon. And the claim is that if you compute this diagram, okay, you will have to use some regulator, because otherwise you will just get nonsense out of it. It's just a divergent quantity. It is UV finite. This is something you expect because the theory itself is UV finite, but it has infrared divergences. Okay? And this is also something that we could have anticipated, because what is the origin of these divergences? It's the physics is relatively clear here. So we are doing some scattering experiment. I don't care about what is happening in the middle here. It's like some sort of hard scattering, out of which some gluons radiate outside. Okay, but these gluons, they can still interact even when they are far away from one another by exchanging other gluons. Okay, and this is possible because the particle that we're exchanging is massless, and so there is a long potential, if you want, which is a long-range interaction. So how do we deal with this kind of things? Well, this guy is soft. Again, it's a long-range process as compared to the momenta of these two gluons. So what we can do is we can apply a iconal approximation. So what is the iconal approximation? The iconal approximation is a replacement of this gluon by some Wilson line. Okay, so I have two Wilson lines. Okay, one for my gluon P1 and the other one for my gluon P2. The idea being that because these guys are hard as compared to this possible gas of soft gluons that they are exchanging, they do not recoil. Okay, there is no recoil. It's not like they get deflected in another direction. They keep going forever along their classical trajectory. And for this reason, it is possible to replace them by a Wilson line, which, as you know, is a way to introduce an external probe, a classical object, in a gauge theory. Okay? And what is important here for us is that these Wilson lines are like-like. Because the trajectory are like-like. So this is a very same picture as Collier drew yesterday. You remember he had something like this. So in this case, he wanted to be very cautious. So it also put another point here to make the full object gauge invariant. So in our case, we are not trying to do something like that. We neglect for the moment possibility of non-gauge invariance. Okay, we could even put some cutoff here. It will not be gauge invariant quantity, but it's not going to play an important role because the divergences that we care about are localized at this cusp. Okay, they essentially come from the exchange of gluon at this cusp. So in the case of Collier, this angle was Euclidean. It was parameterized by some phi. So you remember this gamma cusp of the top coupling times some angle phi. And he explained to you how to compute this cusp at small phi, which is the so-called BPS limit. Here we are interested in a limit where this angle is like-like. Why does it mean that the angle is like-like? It means that we should take large imaginary value of phi. And in this case, it is known that this object scales linearly with phi, with an object in front that controls the scaling, this linear scaling, which is just a function of the coupling. So this is the cusp anomalous dimension, which is appearing here. Hopefully it will become, it is perhaps already clear for you why now it is appearing. It's just a function of the coupling, and it is what controls essentially the divergences. The claim being that if you take this Wilson loop, so now I guess you should know very well what the definition of the Wilson loop is. Take the trace of the partial order exponential of the gauge field, it's not a closed contour. And the contour that you choose to be the cusp. Okay? And the claim is that this object here, which I call W cusp, has some divergences, which I should regularize. What I do is that I take my cusp, I replace it by two lines here. So here there is an out cutoff. Here I put the length cutoff also, okay, because I can have, this is an object which has no scale in it. Okay, so I can have divergences coming both from short distance and long distance, but they are essentially equivalent to one another. So I introduce two cutoffs. Let me write it down. The nav cutoff, which I denote by lambda. And if you want to think about it in terms of the original scattering problem, it is nothing but the Mandelstam invariant in this channel. So it is minus P1 plus P2 squared. Okay. And I also want to put some short distance cutoff. Some long distance cutoff. L, which is 1 over mu, if you wish, from the point of view of the regulator that I was using here. Then the claim is that to any value of the coupling, the log of this W cusp will take the form 1/2 gamma cusp times the log square of log L times lambda. Yes?
Could you explain again this picture with regularized contour?
Yes?
There is some circle attached to
Oh, sorry, yeah, it's very sketchy. So what I'm doing is that I want to avoid all the points which produce some divergences. So like in this diagram, the points that produce divergences are the point at 0 and the point at infinity. Okay? So I'm not working in this compactified space. So Collier was working essentially on the sphere after compactification. Here I am on Minkowski. So what I do is that instead of integrating from So what does it mean to have this kind of contour? It means that you should integrate from 0 to infinity. Instead of integrating from 0 to infinity, I remove a piece here. So I will integrate from some cutoff, which is 1 over lambda. This is a short distance cutoff, up to some long distance cutoff, which is L. Okay? So this way I'm only integrating over a finite interval, which of course becomes very, very large, and which gives me this double logarithmic behavior. So the reason I'm spending some time on it is that I guess some of you might not be familiar with the fact that we have a double log behavior. So you are, I'm sure, all familiar with the fact that there are trivial divergences in quantum field theory, and this gives rise to some log, and the coefficient influence of the log measures the scaling dimensions, the anomalous dimension, and so on. So here it's not the case. You see, we have a double logarithmic behavior, and this is typical of these infrared divergences. And there is a very simple reason for that. If we use this Wilson-Wood picture, which is related to the symmetries of our cusp. So can somebody tell me what are the symmetries of this cusp? No, still need some time to wake up. So there is a boost symmetry. So this is like a icon in 2 dimensions. So there is a boost symmetry. And plus minus. Okay? And this is a boost. And another one. No? Dilatation. Okay? So if I rescale things like this from bottom to top, this does not change my contour. I can combine them in a different grid if you want. I can introduce a generator which I will call d sigma. It is 1/2 d plus minus, and d tau, which is 1/2 of d minus n plus minus. So one essentially, so these are of course related to Lycon coordinates. So my Lycon coordinate is u plus equal t minus x equal exponential to tau, and u minus equal t plus x equal exponential to sigma. So this generator just move things like this or like that. Okay, so they are just translation if you want, but they are translation in this Lycon coordinate. Okay, this is as simple as this. And then you might guess that if you want to write some sort of invariant measure associated to this object, it will be something of the type du plus over u plus, du minus over u minus. And this is exactly what happens when you try to compute your cusp Wilson loop at one loop. You have a propagator here, which is 1 over the inverse distance square. This distance square between 2 points will be the product of u plus times u minus. Okay, there is some factor in front, some g Young-Mills square, and some Casimir, some quadratic Casimir for the color contraction, some pi square, minus apparently, and then there is some integral, which you immediately understand is ill-defined. So we need to put this cutoff by hand, 1 over lambda to n, again, get somewhere here, just have something in the middle that does not touch this boundary. Okay, and this now it is straightforward to see that it will give us a double logarithmic behavior. Well, this g is the same g as Folliard used. Okay, so it's just a rescaling of the Taft coupling. Is it clear?
In this relation there, when you say iconal,
Yes.
it's not completely clear what you mean.
It's not clear? Okay, I'm sorry. So I tried
This is
to.
a Feynman diagram on the left-hand side.
This?
Yes.
This is a Feynman diagram, so
How
a
do
very
you
sketchy
connect
one.
to
But
that? How do you show that this is equal to that?
how do I show that this is the same as this? So this is not exactly the same as that. Obviously, here there is a lot more information that is not captured here. Okay, so here there are many particles incoming, they carry a lot of information, and I'm just dropping everything. The reason is that I'm just interested in describing for the moment the processes which give me infrared divergences. So what I was trying to explain is why do we get some log square divergences here.
And that is ultraviolet cutoff, the lambda.
In this picture, everything is okay. Let me be okay. You won't be happy probably, but I will put 1 over epsilon square, okay, which is dimensional regulator. Okay. Why I'm doing it? Because okay, in this way it's not clear where it comes from. But it could be UV or infrared. So for the amplitude, from the amplitude point of view, the divergence comes from infrared effect. Okay. So this integral is UV finite. You don't
So
need.
the amplitude is ultraviolet finite.
The amplitude is UV finite, you know why? Because the theory is UV finite. So there cannot be UV divergences because if there was UV divergences, you would not know how to interpret them. Because there is no room in the theory to absorb UV divergences. Of course, you need to preserve supersymmetry, blah, blah, blah. But so the only problem here comes from the fact that we are insisting that these legs are massless. And so we are forcing the integral to explore some domain where it is not cut off. There is no infrared cutoff. So the integral just blows up. So you need some regulator. Here I'm being very sketchy because I did not write down the details. So, but in this regulator where epsilon is d minus 4, the number of dimension minus 4 roughly, the infrared divergences will manifest themselves like 1 over epsilon square. Okay? And 1 over epsilon square, as you know, this dictionary between this funny cutoff and the more familiar cutoff is that each 1 over epsilon is a logarithmic divergence. Okay? So here the important point, which I probably did not express very clearly, is that this object is a double logarithmic divergence. Okay? Now the goal was to try to explain why we get a double log divergence and not a single log divergence, or why do we get a divergence at all. Okay? And the idea was to focus on those processes which are responsible for this behavior. Because again, here there is some hard scattering. Okay, but this hard scattering we know is totally safe in this theory. There is nothing happening. So if something is happening, it has to do with the fact that we have this massless particle, which can propagate over very long distance and exchange over very long distance. So in a sense, it's like if they were never. It's like if they could never completely get rid of one another. You know, by exchanging these very soft gluons, they can talk to one another, and we cannot really completely separate these states. So this infrared divergences is a manifestation of the fact that this S matrix is actually not very well defined. Okay, after all, what we are talking about here is a CFT. Usually in a CFT, you will not consider a scattering process because you know that this is not the right way of thinking about conformal-field theory. But here we see that the price to pay for being able to talk about an S matrix, and again there is information behind these infrared divergences which might eventually enter into some infrared finite quantity like cross-section and so on, after we properly get rid of this, physically get rid of these divergences. So the price to pay for being able to talk about this amplitude is just to control this infrared divergent part. Okay? And if you control it and can subtract it properly, then you can read out what you will consider as being the finite result, or the interesting piece of the result. Okay? So that was for the general philosophy. And here what I was saying is that if you imagine now you take this pattern, okay, from the point of view of this soft guy, this pattern is traveling has a lot of energy. Okay? And in fact, the effect of this emission on the pattern is negligible. In the first approximation, you will not even consider that this pattern is experiencing anything. It's just following its trajectory, and sometimes it is emitting something around it. Okay? So this is like a dephasing, but this is not like a changing direction. Okay? So if you want to take this effect into account, you are allowed to simplify the Feynman rules for the emission of all this soft gluon. Okay? Essentially keep the relevant part of the vertices here. And this is equivalent to replacing this line here by a Wilson line. Okay? So essentially you want to replace this line by a classical object which follows a classical trajectory. And the recipe, according to Wilson and others, is that we should plug this phase here in the path integral and compute its vacuum expectation value. Okay? So we are replacing a quantum object by its classical description in terms of this this contour.
And the contour is two cusps or one?
No, there is a single cusp, but it is in the adjoint. So each line. So in fact, so here you see for 4 points, what we get is we have 4 sectors. We have 4 sectors to consider. Okay. So one sector here probes the S channel, another sector probes the T channel, this one probes against the S channel, this one probes against the T channel. Okay, the structure of the infrared divergences is between nearest neighbor, because we are in the planar limit. Okay. And it's just decomposing the amplitude into various sectors. And then you can analyze each sector separately, and this is what we did here. Okay? And here, just by noticing some simple fact about the symmetry of the object that we are considering, we kind of understood why we were getting double log instead of a single log.
This formula is connected to that one?
Yeah, it is meant to be connected. It's just that this log square here that we were, the log square is the equivalent of this term here in dimensional regularization. I was just trying to do some hand-waving mapping between the two by saying that there is an hard cutoff, which is essentially fixed by the Mandelstam invariant, okay, which is the energy that came out here, if you want. And there is an infrared cutoff, which is whatever other scale I have in my problem, which is this mu, for instance. So this is very sketchy, so it's not, you should not take it for, this is not a rigorous derivation of anything, it's just trying to explain why we are getting double log. Okay? And emphasize the fact that these double log are controlled by a simple object, which is this cusp anomalous dimension. And if you remember what Collier said, you know that there is a system of equations that describe this cusp anomalous dimension. So we already have some evidence that integrability can be used for computing scattering amplitude, because integrability in particular predicts this cusp anomalous dimension, which controls the divergent piece of the amplitude. Now the question that we would like to answer is whether we can do better than that, and whether we can use integrability for computing also the finite piece of the amplitude. So the finite piece of the amplitude does not care much for the moment about this kind of like Wilson loop. But as we will see in this theory, there is even more relationship between the two objects.
But at one loop, this cusp anomaly should be well defined, should be your analytic expression.
Yeah, so at one loop it's essentially what I wrote here. So at one loop, gamma cusp is 4g squared. Okay? Then it receives some correction and so on. Okay? But this we can consider to be known through integrability. Actually, there is the equation that Collier described yesterday is really it's really not the right way for computing this quantity. It's a very complicated set of equations. So the equation, the first time an equation was proposed for computing this object was through the work of Weisert, Hidden, and Stodacher, and it is known as BES equation. So the BES equation gives a description based on integrability of this cusp anomalous dimension at any value of the coupling. Okay? So if you combine this prediction and this ansatz by BDS, then you believe that you have already solved your problem. because everything here is controlled by a one-loop diagram. Okay? So don't take this for literally as written. Just take this diagram as a definition of what should stand here. And the recipe, roughly speaking, is to replace the coupling by this cusp anomalous dimension. This is the least we can do given the fact that we know from the very beginning that the infrared divergences are controlled by this cusp. And so they will receive correction, so one loop is not enough. We need also to dress the coupling. But what BDS is kind of saying is that if you dress the coupling everywhere, not only in the divergent part, but also in the finite piece, you get the full answer. And this is rather bold. It's not obvious why it works. But BDS did a couple of checks, loop by loop, for this 4-point amplitude, and they observed some iterative pattern. So when you go to 2 loops, you will have double box diagram and so on. And a lot of new topology appearing at higher loops, this tennis court and whatsoever. So they did the analysis, you see all this, which for them was a way also of testing some new method, so-called generalized unitarity method, for computing more efficiently Feynman diagrams. Okay? So they developed this formalism, they applied it here, and what they found is that the result wanted to exponentiate up to this small redefinition of the coupling. And then they say, okay, let's say that it's true all the time and for everything. Let's say it's true for 5 points or so, let's say it's true for n equals 5, 6, 7, 8, 9, 10, and so on. And they propose this BDS conjecture or BDS analysis. Now the question that we will address in, I think it's the right time for ending. The question that we will address in the second lecture today is whether it's a reasonable assumption or whether they miss something. And if they miss something, what it is and how can we correct or fix this nonsense. Thank you.